gauge transformations on wave functions. And later we will also start doing angular momentum. So in electromagnetic theory, we have gauge transformations. So these are transformations of the potential and the vector potential such that the electric and magnetic fields remain unchanged. Yes, so that's we know from electromagnetic theory. So if we add a constant to the potential V, like we have here, we take a constant V0, and we add a gradient of a scalar field to the vector potential, then the electric fields and the magnetic fields are not affected by these transformations. So these gauge transformations then preserve the electric and magnetic fields. So the questions we would like to ask now is what happens to the wave functions? So we kind of expect, since the physical fields, the electric and magnetic fields are not affected, then the wave functions would probably just gain a phase factor in front of it, because we expect that expectation values of observables should not be affected. So let's see what happens here. So let's start with just changing the potential, adding a potential by constant. Yeah. So we have then two Hamiltonian, H and the H tilde. So they differ just by this constant here. And let's have a look at the evolution of a state. So let's say that time t equal to 0, we have state given by this psi at t0, and we look at the evolution of the states under the gauge transformation. So we evolve the state using H tilde. So this is our time evolution operator. Since V0 is constant, well, then it commutes with the Hamiltonian. And so then we can just, there should be a hat here. I think they're only a hat somewhere. So then we can just take out the V0 from the exponential. So we just get this phase factor here. And this one here is just the state without the gauge. Yes, that's the original Hamiltonian. So that just evolves the state from t0 to t. So then we get this result here. So the wave function, as we expect, under the gauge transformation, is just a phase factor multiplied by the original t wave functions without the gauge. So more interesting, however, is when we consider change in the vector potential. So we make a gauge transformations on the vector potential. Then things are a bit more complicated. So first of all, when we have a charge particle moving in the electric field, moving in the magnetic field, then we have to change the momentum from P to P minus EA divided by C. So I have this in the appendix. If you have forgotten where this comes from, you can have a look at the appendix. It is derived in the appendix, how you go from P to P minus E upon C times A. So this is what we have to do. So let's see what happens to the wave functions when we do this transformation. So we have the Hamiltonian in general that will then be equal to kinetic energy. So we have to replace this is squared plus E phi. So phi is the potential. So this momentum here is usually called the kinematic or physical momentum, if you like, kinematic momentum. So whereas this P here is the canonical momentum. So that's the terminology. So the canonical momentum is the one that fulfills the commutation relations with the position operator, whereas the kinematic momentum in general does not. So we want to see how the wave functions now changes under these gauge transformations, and the result is given here, and we will work it out. So again, it will be just a phase factor times the wave functions without the gauge. So let's see what we can do here. So let's consider the eigenvalue equation for the kinematic momentum. So this is the physical momentum. So these are all operators, of course. Yes, I don't want to have too many signs here. So let's call them eigenvectors, eigenfunctions, chi p. So this has some eigenvalue, EP, call it. So this actually should be a vector. So I didn't have the vector sign in the notes, but it's kind of clear. Yes. So now we make a gauge transformation. So then according to the formula, we must add a gradient of a scalar field, call it lambda, and we have a new wave function, call it tilde. And then we argue that we are looking at the kinematic momentum. So then the eigenvalue of this kinematic momentum should not be affected by the gauge transformation. So then we should have the same eigenvalue, chi p, tilde here. So since chi and chi tilde have the same eigenvalue, so we expect then there should be some phase factor, call it f, times the original wave function. So f here is a phase factor. So let's see what happens if we now use this form in this equation here. So we have P minus C A minus C plus C gradient lambda acting on F chi P like that. So I drop the position vector, just we understand this all depends on chi P like that. So the aim is to figure out what is this phase factor F is. Yep. So now we have to be a bit careful because the P is the momentum operator, and in the position representation, that is a gradient. So when we operate P So let me put it here, maybe. Put it here. Okay. So if you operate P on the product of F and chi P, so that would be equal to F chi P plus chi P. So this is the operator. Yes. Because the P is a gradient in the position representation. So then we have PF here. So let's just call it vector like this. We understand these are operators. PF then chi P. And then I have F P chi P. So that's from the P. And the other terms are just multiplicatives, so that's relatively simple. Just plus on C, the whole thing. So that's equal to EP P like this. So if we arrange things a little bit, we then get PF chi P that minus C. So I'm just collecting the terms in a slightly different way because I want to make use of the other equations when we do not have the gauge. Like that. So now we see that we can use this equation here. So that is equal to EP chi P from this equation here. So then this thing goes away in that one. So that means that this thing is 0. So we have not specified what this chi P is. It can be any eigenvector of the mental operator here. So then we should have PF minus EC, okay, times F. Is that correct? Yes, equal to 0. So if we replace the P with a gradient, this becomes minus IH bar gradient of F is then equal to U C times F. Well, this is just a first order differential equation, and we can solve this so that the solution is just this exponential. Like that. So that's exactly what we had in the beginning. So what happens then to the wave function when we do this gauge transformations on the vector potential is that it obtains a phase factor given by this one here. So unlike the potential case, the phase factor here does not depend on time. It just depends on the position. Because this function lambda is a function of position. You can also just take this form of the wave function. So let's see. So let's state then comes. So we have done this for the phantom breakdown, but we notice that this phase factor here does not depend on the eigenstates of the kinematic momentum. And so it should also apply to an arbitrary wave function, because I can always expand an arbitrary wave function in terms of the eigenstate of the momentum. So then this is also true for an arbitrary wave function. This is the final result we get. One can also just use this form here and verify directly by using it in the Schrödinger equation. So if you plug this into the Schrödinger equations with the gauge transformation, then you will find that this state fulfills the Schrödinger equation. That's another way. Okay, so this is gauge transformations. The magnetic field can actually induce interesting phenomena in quantum mechanics, especially because of this presence of phase factor. So there is a very interesting phenomenon due to the presence of magnetic field. This is called the Aharonov O effect. It's called Aharonov O effect, yes. So this is actually a nice example also for the path integral formulation. It can be understood nicely in terms of the path integral. So this effect here is the following. So let's say you can also read this in Sakurai. It's a nice description of these phenomena in the book. So just reproducing the figure here. So here we have a double slit experiment like that, and we have some source here. Let's say we have an electron source or any other charged particle source, and we have here some screen on the right hand side. So if we put some magnetic field here, and so the magnetic field is, let's say, this going towards us. Doesn't matter whether it is down or up. So we have this magnetic field here. That's a field, and the magnetic field is completely confined in this cylindrical region. So you have to imagine that this is a cylinder. It's like a solenoid, yes, perpendicular to the plane. So the magnetic field is essentially confined to this region. And now we look at what happens. We make an observation at the other side. So this is just a double slit experiment, except that we have this magnetic field, and we want to see what happens with the interference here in the presence of this magnetic field. Now, if we think about this in terms of a path integral, then first to look at the Lagrangian. So the Lagrangian under the presence of magnetic field or vector potential becomes the original Lagrangian. So let's say call it L0 here, plus term like this, dt. So that's the velocity, that the vector potential. So this is what we have to do. We introduce a vector potential into the Lagrangian. I think you can also find this derivation in many textbooks. Yes. So this means that the action, so if we look at the action from two neighboring points, n and n minus 1, this will be the original action plus this extra term. So that will be plus c integral tn minus 1 to tn dt. That's the action. And dr dt dot a. Okay. But this is just an integral from xn minus 1 to xn of dr dot a. So then, if we sum this up over the path, so we imagine we have two paths here, one going like this, say, and another one going like this. So we have paths, let's say C1 and C2. So then this additional term will introduce phase factor. So we will get exponential of IE divided by h c, integral from, so we call this x0 and that xn, let's say xn of dr dot a. So these are of course vectors, yes. So this is the additional phase factor that arises due to the presence of the magnetic field or the vector potential. So if we consider now these two paths, the C1 and C2, then we realize that the phase factor and C1 and C2 are different because if you think about this magnetic field here, the corresponding vector field would be kind of around it, okay? Because the B is given by the curl of A. So the B is perpendicular to the plane, so then the vector field is kind of going around it, yes, like this. So the vector field is not zero outside this region, although the magnetic field is zero. So if we look at I always have this problem here. Okay. Okay, so if I look at phase difference between these two paths, then we find that this is just given by H bar C. So these are the phase here. Looking at this phase here. Look at integral from x0 to. So let me just call it C1 and C2. So let's say this is C1. There will be dr dot A and minus C2. So this comes from the interference effect because we are looking at the probability. So we take the square of the propagator. So this when we sum two terms, then we will get interference term. So these are just the interference term. This is the interference term here. So we remember that in the path integral formulation, we add the contribution from each path. So here I'm looking at the C1 and C2. So we have contribution from C1 and C2, and then we take the square to get the probability, take the modulus square, and then that will give me this interference term. And we notice that this is just equal to, let's see, of line integral of A around this loop, C1 and C2. So C1 like this, and then go back on that. C. So let me call it then C1 minus C2 because we are going backward in the case of C2. So that's minus C2. So it forms a loop. And we know from Stokes theorem. So if I have B dot ds, so the S is the area, so that will give me the flux of this magnetic field here. So that would be equal to integral of curl of A dot ds, and I can use the Stokes formula here. So that becomes A dot dr around the loop C. So we see then this is just equal to H bar C times the flux, the magnetic flux. So it's not zero. So this means that we will see some effects of this magnetic field on the interference pattern that one see in the screen here. So if we change the magnetic field, then one should see a change in the interference pattern because this interference term is not zero, it changes with the magnetic field. The funny thing about this effect is that the particle actually never goes into the region where the magnetic field is finite. So the magnetic field is entirely confined in this region here. And so the particle actually never enters into that region where the magnetic field is not zero. Nevertheless, we can see the effect of that magnetic field, very physically observable effect of the magnetic field. Even though the charged particle does not experience Lorentz force, for example, because it doesn't go into the region where the magnetic field is not zero. So it is a kind of difficult to understand, perhaps. So it also raises a kind of fundamental question as to which is more fundamental, so to speak. Is it the magnetic field or is it the vector field? So the vector field is not zero outside, but the magnetic field is zero. So is it then the vector field which is more fundamental, not the magnetic field? I don't know the answer. So I don't know what you think. It's interesting. I think it's like an action at a distance. It's a bit like later when we consider the spin correlation measurements, this entanglement. That, if we have 2 electrons, let's say, with a spin up and spin down, and then, we will do that later. So there's a kind of action at a distance here. Okay, so that's one example. I didn't have this in the notes, but you can read it in the book. I thought it could be interesting to discuss this here.
Can I ask a question?
Yes.
This also gives us the magnetic flux is quantized, right?
Well, I mean, this magnetic flux is just a classical magnetic flux.
Oh, directly classical magnetic flux. Okay.
Yeah, so I just have a solenoid, yes.
Okay, thank you.
So I think you're thinking about situations like the quantum Hall effect or something like that.
Yes, I was just trying to find a relation. Maybe can be coming because whenever thank you.
I mean, the magnetic field itself is not quantized. I mean, it's just a magnetic field. I mean, that's from the solenoid, so it's classical magnetic field.
Yeah, of course, because we use the classical Lagrangian in the action. Okay.
Yes, that's right. So this Lagrangian is entirely classical here. So I should have mentioned that.
Thank you.
So that's the nice thing about the path integral formulation, that you have a classical action. So it's like a number, so you don't have to worry about non-commutativity. Yes, if you have operators, and you have to worry about the possibility of having non-commuting operators. But in the path integral formulations, things are written in terms of classical actions. With the price you have to pay is that you have to sum over all these paths going from one point to another. So you can also solve this problem using the Schrödinger equation. You just solve the Schrödinger equation, but it's more intuitive thing using the path integral formulation rather than the Schrödinger picture. They are, of course, equivalent. Yes.
Thank you.
So the choice of a particular method or way of doing things is usually very important in physics in general, I think. If we choose the right coordinate system, then things become very simple. I mean, you can imagine that you want to solve just a classical problem of a pendulum, let's say. If you choose the angle between the hand of the pendulum and the vertical axis, that will give you a very simple equation, just a harmonic equation, second order differential equation. But suppose that you choose some funny coordinate systems, like some tilted ellipsoidal coordinate system, let's say, then your equation of motion looks horrible. Yes? and you don't recognize immediately the solution because they are equivalent. But it kind of illustrates that the choice of your coordinate system, of your method, of your approach, it can be very important to see what's going on in the physics. Okay, so I want to continue now with angular momentum. I know that you have done this angular momentum in previous courses, so I will try to skip some of the basic things. So, angular momentum. So we want to do angular momentum in same way or similar way as the one we did with linear momentum and with a time development operator. So we have, let's consider this first in angular momentum in the real space. So we have L is given by R cross P, and later we generalize this to spin also. Now we have, of course, the fundamental computation relations. So that is Li J is equal to K H bar K. That's the well-known commutation relations among the angular momentum operators. Now, this angular momentum operator is actually a generator of rotation. Yes. So I will show this, I will verify this. So the infinitesimal rotation, infinitesimal rotation. You have an operator like this, and you have some axis m and some angle d phi. So we make a rotation around the axis n and with the angle d phi. So that is given by 1 minus L to n like this, divided by h bar d phi. So we see that we have a similar form as the one we had for the translation operator and time development operator. So here is the generator. So the angular momentum is the generator of rotation. And if we have finite rotation, call it phi here. So it's a finite rotation, and it will be just an exponential, which you can get by simply applying the infinitesimal rotation many times, yes, like we did before. So let's first check that it is indeed a rotation operator. And one way to do this is simply apply this to some position eigencat. Let's take position eigencat R like that. So that would be x, y, and z. We look at the Cartesian component. And we apply this to an arbitrary. We applied this infinitesimal rotation. This onto to this state here. So we can choose the n to be along the z-axis without loss of generality, shouldn't matter whether it is Z or some other axis. So then this thing becomes, so this becomes just 1 minus I Lz upon h bar and d phi, like that. Okay. And Lz is, of course, equal to x py minus y p x. It's from this one here. Yes, we are looking at the z component of that. It's just given by this operator. Okay, so now we apply this to this state here. So that's an arbitrary state. So we get 1 minus so we first recall that from the previous result, we have the following result for the translation operator. So p dot dx is of course just px dx. So this is of course that's px plus the py dy and so on. This hat. So then we see that the px will shift the component of x by dx and the component of y by dy and the component of z by dz. So that's what we had before for the translation operator. And we also recognize that the x and the py 0, and also the y and the px is equal to 0. So we can commute x and py and also y and px. Okay. So then if we apply this operator here onto the position eigenket, so let me that. So we get 1 minus I z upon h bar d phi acting on there. So that's equal to x py minus y px. So that's our Lz. It's divided by h d phi. Yeah, like that. So we have so I can commute x and py because they commute, so then I get pyx like that. And the same with the second term here. So I can commute, not commute, y and px, right? Divided by h bar. Thing on that. So now we know from the translation operator that py will shift the y coordinate. Well, first of all, I have to apply this position eigenvectors x and y, and so that will just give me x and y. So I can just get rid of the hat. And so let's get rid of that and that one, because this is an eigenstate of x and y. So I can just replace the x hat with the number x, and the same with the y. So now we can see that the py will shift the y component by x d phi divided just x divided by not divided by, multiplied by d phi, whereas the px will shift the x component by y dy by y d phi minus y d phi. Yes, because we had it before. I think translation operator. So we get 25 here, and we have y plus x d phi, and the z is unchanged because we do not have any z. Then we just have z. So that makes sense because we are rotating around the z axis. We don't get that. No? So let me continue a little bit, and then we can have a break. So this state is actually just a rotated state. We think about this in the xy plane. This is xy here. And you might think about it as a vector like this. Then the rotated vector is just that one there. And we can see this more explicitly by writing the position as x plus iy. So that can also be written in terms of the radius times the radius exponential of the angle. So the rotated one will be the rotated one, so that will be a prime. Or 0 is still the same. So that will be I phi plus d phi. So that becomes then R times the d phi, like that. So if we just consider this to first order in d phi, then we see that x prime plus y prime is just given by, so we use it here. Then you get x plus iy, so that's r, times the expansion of that Taylor expansion to first order. So we're looking at infinitesimal rotation, so we keep the first order. And we see that can identify that the x prime is equal to x minus y d phi, whereas the y prime is equal to y plus x d phi. Yes, that's exactly what we have here. So this operator does indeed rotate the state by an amount d phi around the z-axis. So we have convinced ourselves that this is indeed the rotation operator. We could, of course, work backwards from the wave functions, or from the state, but that is a bit more complicated. It's the same thing. Yes. Okay, so we have a bit of time here, 5 minutes. So maybe we can have a break. We start, let's say, at 20 past, because we are a bit over. Okay, and you have questions, and I can also try to answer your questions if you have any. So if there are no questions, then we'll meet again at 20 past, not a quarter past, but 20 past. Okay, so let's continue with this angular momentum thing. Yes, so we've just shown that is operator corresponds to rotation. So that's corresponds to rotation by angle phi around axis n. So we have considered this this rotation in real space. So we have angular momentum in real space where this L is equal to r cos b. But we also know that there are quantities like spin, which we of course cannot write in this way here. But nevertheless, we know from experiment that it behaves like very much like angular momentum, because it's similar to magnetic moment. So we make a postulate or an assumption that this rotation operator is also valid in spin space. So we say that in general then we have rotation operator like that, where this J now can be L, or can be S, and can be some other angular momentum like operator. And as we already know, this J has this commutation relation. Okay, like that. And we also know that J squared, so J squared is the Jx squared plus Jy squared plus Jz squared, commutes with all the components of the angular momentum operator. So this allows us to have a common eigenstate. So usually labeled with Jm. So that's Jj plus 1 h bar squared. Yeah, like that. And we choose one of the component, which is usually the z component. So that's equal to h bar Jm. So this implies here the fact that J squared commutes with all the components means that we can choose one of the component and label the eigenstates of the angular momentum states with J and M. So it's defined in this way here. So actually, this type of algebra here, where you have a set of operators that fulfill this kind of commutation relations, is from a more general picture. This is usually known as the Lie algebra. So maybe I should erase this. So we have Lie algebra. So I'm trying to give a kind of more general picture of this angular momentum operators. That is actually an example of what is known as Lie algebra. So in the case of Lie algebra, generally we have a set of operators. I call it X here. So we have X, I, X, J. So that's in general can be some linear combinations of ij. So these are just some coefficients, usually known as the structure factor. So this is a bit of an aside. Yeah? But I thought it could be interesting to talk about it. I think some of you already know about this. You do group theory. So these sets of operators are generators of a Lie group or continuous group. So for example, if we look at angular momentum, and we see that this structure factor, this Kij, would then correspond to the Levi-Civita symbol. Yes, Ijk. So that's the Levi-Civita. An example. And the group, in the case of angular momentum, is the rotation group. Because if you multiply the rotation, then it will just give you another rotation. So I will use the rotation group or the angular momentum as an example of this. This structure factor has the property that it is antisymmetric in the lower index, and then we can form a symmetric quantity in this way. Okay, so I'm summing over K and L, and this is you can easily see that this is symmetric in J and I from the fact that this antisymmetric.
You should change I and J in the
sorry.
below. I should change, I'm sorry. You wrote it's antisymmetric, but you...
I'm sorry, yes. Yeah, sorry, you're right. Thank you. That, of course, should be JI. Yes, thank you. Okay, so now we define this matrix G. We can also define the inverse of this matrix. So define the inverse of that matrix. Like that. And then we can show that if we form the following operator, so this is now the inverse of this matrix here. Okay. This operator commutes with all the generators. So in the example of angular momentum, then this C will be just the J squared. So it's usually known as the Casimir operator. I have all this in a separate note. I think it's called Lie groups. If you look at the directory, you will find this Lie groups.pdf. I have all the details, so I'm not going to derive it here because it's quite lengthy to show that this is equal to 0. So I'm just trying to give a kind of general picture of what we are doing here from a more general perspective. So that's the Casimir operator. And it turns out that one can redefine the generators in the following way. So we can collect a set of operators. I call it HI here. So HI here is just sum of the X operators, the generators, that are mutually commuting. So they are mutually commuting. So in the case of the angular momentum operators, then there is only one mutually commuting operators, because it's kind of clear from the commutation relations that if I take, let's say, Jx and Jy, that will not be 0, and Jx and Jz will not be 0. So it only commutes with itself. Yes. So, and that we choose to be the Jz. So example will be the Jz in the case of angular momentum. So the number of mutually commuting operators is usually called the rank of the algebra of the Lie algebra. It's not important; it's just a name. So the point is that we can do this. We can select, we can collect mutually commuting operators, and then we have the rest of the operators, which I call it E lambda, E alpha. So E alpha will be some linear combinations of the rest of the operators. So this can be written as, this is the rest here, can be written as ladder operator. As ladder operators. So if again, if we take the angular momentum as an example, then we have this J plus and J minus. So that's Jx plus minus I Jy. And also in addition, we have a kind of set of Casimir operators. So can be proven. I think that we're not going to do it here, but the number of Casimir operators is related to the rank of the group. So this means that since the Ci here commutes with the H, we can then, or with all the other generators, then we can choose simultaneous eigenvectors of the Ci and the H. Yes, we choose that operators H as the mutually commuting operators, simultaneous eigenvectors of the Ci and Hi. So this will be, in the case of the angular momentum, this will be the J square and this will be the Jz. So there's only one mutually commuting operator in the case of angular momentum. So we have then Ci, I can label the eigenstate with the eigenvalues of the Casimir operators and with the Hi. So like that. Yes, so it is very similar to what we have with J squared acting on Jm. So that gives me the Jg plus 1, J squared Jm, and we have the Jz Jm like this. So now we want to show that the rest of these operators, the rest of the generators, can be written as ladder operators. So it's a general result that you can always write it like this. And to do that, we note that we want to solve this kind of eigenvalue problem. Like that. So this thing is a linear combination of the operators. As J. Alpha like that. Now we used this Lie algebra. So then we get sum over kj, let's say, that give me xk. Give me ckij. So that's from the Lie algebra between h and xj. Yeah, that one. So we can rearrange this equation to give me ck, sub j, ck, ij, eigenvalue. Then I need that conical delta. Yeah, that's 0. So then this thing must be equal to 0. So then we have an eigenvalue problem. So this is as the eigenvectors. So this aj alpha are the eigenvectors of the structure constant. This structure constant C. So you can check this for the case of angular momentum. So you have the structure constant is just a Levi-Civita symbol. So if you find the eigenvectors of that according to this equation here, then you find that you have the property that is E alpha has the property of a ladder operator. Yes, so this is very much like you have in the case of angular momentum. So you have H plus minus is equal to plus minus H bar J plus minus. So this will be this HI here, and that would be the E alpha. So that's the E alpha. So this is a bit like a more abstract form of eigenvalue problem. So you have a commutator instead of a usual operation on a state. So and then it's easy to show that if you have this property here, then the operator E behaves indeed like ladder operator. So we operate it on state like that. So we use the commutator here, then we get hi minus hi. So that's the eigenvalue of the hi. Is the same thing. So then the hi is equal to hi plus like this. So we say that the state is the eigenstate of hi, but with an increase eigenvalue epsilon I alpha. So that's exactly what we mean by the ladder operator. Okay, so I'm just trying to give the connection of these angular operators to a more general algebra. So this is the Lie algebra. This is a bit of an aside, but if you're interested in the detail, you can read in this separate notes I have on the home page. Okay, so in the remaining time, I would like to start with the spin half systems. So I think you're also already familiar with spin half system. So conventionally, we choose Sz as our choice of base vectors. So we choose the eigenstate of Sz as our base vectors. So we then have a two-dimensional Hilbert space, spin up and spin down, with eigenvalue plus h bar upon 2 and minus h bar upon 2. We have here. So as we recall that we can expand, we can write operators in terms of eigenvectors. So let's say phi n is the eigenvector, phi n are eigenvectors of an operator A. Then we can do the same for this Sz operator. So the eigenvalue is just plus and minus h bar upon 2. So we can write in this way. So this is one way of writing the Sz. And this can usually define the Pauli operator or Pauli matrices this way. So that's my sigma. So if we look at the matrix representation of sigma z, then it will be just diagonal like that. So that gives us the Pauli matrix. Now we can also work out the xx and the sy from the commutation relations. So you already know this, I think. So the result is just given by this here. Yes, so that corresponds to sigma x. If we look at the matrix representation of that, so that would be 1, 1 there, 0. And so y would be, put the I here, then it would be 1 minus 1 here. Or maybe we can just get rid of the I here and put it the matrix, so that would be minus I, and this is plus I think. Yeah, it should be plus I, like that. So these are the Pauli matrices. Then we can form this ladder operators, as we just discussed before. So it's a very useful operators because it allows us to go from one eigenstate to another with different z component of the eigenvalues. And a S set is particularly a simple form. So if we look at the S plus here, then it will have this matrix representation, and sigma minus would have like that. So kind of easy to remember. Of course, the S plus and S minus and the SZ are equivalent to XX, SY, and SZ. Yes, because these are just S plus and S minus are just linear combinations of XX and SY. So we can always go from one to the other. Okay, so this is the basic properties of the spin, that spin half. So now we want to look at the rotation in this two-dimensional Hilbert space of the spin half states. So I think that's all I have. So we want to look at the rotation in the spin half. Hilbert space. Okay, so we just write our rotation operator. Then, as we said before, we generalize the rotation operator to the spin. So then it will be just minus s dot n here divided by h bar phi. So it's more convenient to work with the Pauli operators. Divided by 2 phi. So we get rid of the h bar. Now we want to work out then the explicit form of this rotation operator. So the simplest way, is the one that I think is simplest, is simply to expand this, expand the exponential. So that then gives us 1 minus n squared squared. I'm looking at the even terms. And then I look at the odd terms. That would be so these are just a straightforward expansion. Like that. So let me just continue. So then we use the property that and this square here. So the Pauli matrices has the property that is equal to a squared like that. So then this thing here is just equal to 1. Yes, because n is a unit vector. So this means that the even term becomes simply a cosine. So that's the expansion of cosine in phi by 2 times the unit matrix. It's a matrix, unit matrix, minus I, and then we have sine here by 2, and like that. So that's because I can take out again, and I have this squared here. Yes. So all this sigma dot n squared becomes 1. So then I'm just end up with sigma dot n. So we can just plug in the Pauli matrices. These are just the Pauli matrices now. So that becomes then like what I have in the notes. So let me just write it down. So it's basically just plugging in the Pauli matrices. I don't know if I have to write all these things. Okay, let me do this quickly. 2 and cosine phi by 2 sine z. Like that. So that is the explicit expression for the rotation. So I shouldn't put the hat there because it is now in the it's a matrix, not an operator anymore. Phi here. This is the explicit expression for the rotation operator in spin space. Sometimes this is labeled with 1/2 like this. So to indicate that it is a spin half. So that's the spin half representation of the rotation matrix. So the rotation matrix has an infinite number of possible representations depending on which angular momentum states we use as the basis. So this is the two-dimensional version, and that corresponds to spin half states. In general, we can choose other angular momentum states. So if we have j equal to 1, so that would be like the p states. If you do atomic physics, j equal to 1, then there will be 2j plus 1, so that would be 3 basis vectors corresponding to px, py, and bz, and pz. So then you have a 3 by 3 representation of the rotation matrix. Now, what I want to do here. Okay, so then we have time. Okay, we can try. So let's apply this rotation matrix to find the eigenstates of the spin operators, spin-off operators, along an arbitrary direction in space. So we know, of course, there's the eigenstates along the z directions, but what happens if we want to know the eigenstates along an arbitrary direction in space? So the easiest way is just diagonalize this this matrix here, because that will give us then the eigenvectors along an arbitrary direction n, and angle phi here. But we can also do this in a more kind of pictorial way by using this rotation operator. So there are two ways of doing this. So we take from the matrix, we take its direction n, and we just take the dot product of that, so that will give us the component of the spin operators along n, and diagonalize this matrix. So that's one way of doing it. And the second way can be done by doing this rotation. So what we do is, let's say that we want to know, this is z, this let me see, this is x and this is y. So let's say that we want to know the eigenvectors along this direction and here. So let's say that if we look at the projection of this, so we look at this station here. So let's say this angle is equal to beta. So that's the same angle here, beta. Then we can start with the spin up eigenstate along the z direction. So start with a state along the z direction, and we make a rotation around the y-axis. So that will be then to the minus y on each part by an angle beta. So we start with a state here along the z direction, and we rotate by an angle beta. So this is alpha. Then we rotate it again with angle alpha around the z-axis. So this should be z. So all we have to do now is just use the matrix representation of these two rotation operators and operate it on the side state phi. So that's the state 1, 0. And this is given by cos beta upon 2 minus sine beta upon 2. So, and this one is a simple form thing. It's just minus sine alpha upon 2 alpha upon 2, like this. And then we just act it on 1, 0. So there we get the eigenvectors along the n direction. So it's quite simple to do it this way. So let me see, we're running out of time here. So let me just write down the answer here. So then we get cos beta upon 2 sine alpha upon 2 beta upon 2 alpha upon 2. It's just found by multiplying these matrices. Okay, maybe we should stop here. So I will repeat again next time, because we are a little bit in a hurry, maybe. So we will go through this again in next time we meet. So I guess there are quite a long break. It's something like almost 3 weeks. So let's see if there are any questions so far. Okay, so if there are no questions, I guess we meet again almost 3 weeks from now, actually. And have a good Easter, everybody.
Have a good Easter.
Thanks. You too.
Thank you. Bye-bye.
Bye.
Bye-bye.
Bye.
Bye-bye.